new topic is, okay, I want to talk about something that you guys actually know from the past. So in the past, you guys have solved systems of equations. So today is really not that different. We're solving systems of equations. Okay. So what is a system? Helen? Okay, two equations. It can even be more than two equations, okay, or more than two variables involved. But it's a group of equations where alone you may not be able to find the exact answer for one, but you can find the place where, or the values that make both equations true. What does it mean to solve a system graphically? So I know you guys know, like, oh, algebraically you find these numbers that make them true. What does that mean? So when you normally have, like, if this is your system, okay, when you solve the system, what are you really finding? Alex? Good, where they intersect. So you're used to solving systems like this, and what kind of equations are these? If you graphed each of these equations individually, what would you see on the graph? Lines. They're linear, okay? But now we've brought into play some other types of equations, right? And it doesn't have to be that if I'm solving a system, I have these two lines and I'm finding where they cross. Why can't it be, oh, maybe there's an absolute value graph and I'm finding where the line would possibly cross the absolute value graph? Or maybe there's a parabola and a line, okay, that could possibly intersect each other, and I could find where those things cross. Okay. Or maybe there's two parabolas. And I can find where those things cross. Okay? So now that we've learned some different types of equations and different types of graphs, why do we have to be limited to this idea of a system being two linear equations and we're finding the one place that those lines might possibly cross? Now we can expand our horizons into all types of different shapes. Okay? Now, how did we solve this? One way is on the calculator, which is fine. We'll talk about that in a minute. But how would you solve this without a calculator? If I wanted you to tell me where these two lines cross in this system right here, what type of algebraic work could you do? Addie? You could do elimination. What else can you do? Substitution. Okay? You have some algebraic things and some graphical ideas. So if we have a graphing utility, or if we can graph it by hand and they happen to cross at like a beautiful little point that's right labeled on the graph, right? We can solve by graphing. If not, algebraically, we can solve by either using elimination or substitution. So we can do those same things currently. We just have different sets of equations like we were talking about. So this is our set of equations. And what we're going to do is we're going to solve it algebraically, and then we're going to see how this can be done on your graphing calculator. Okay? So notice that if you have the note guide, there's a little box in this first section of notes for part A, B, and C, where you can write like calculator keystroke notes. Okay? That's like places for you to put which buttons you pushed to do this in case you forget later on when you go to try to do it. Right? But we're going to do it algebraically, which means I expect you to be able to do it by hand. We're going to confirm it graphically, which means I also expect you to be able to perform this operation on the calculator. Okay? So we're going to start doing it by hand first. So what would be an approach to this? What do you think you guys would want to do? Julia? Substitution. Why wouldn't we want to do elimination in this case? When is elimination nice? Yeah, Raymond? You can answer. Yeah. They're not like two lines, right? Two lines, it's so nice to do elimination because you get like the x to cancel out, then all that's left is the y, right? But let's say we added these together right now as they are. The x's would cancel out, right? The 3x term and the negative 3x term would cancel out. But what would we have left in our equation? X squared, and also we'd still have y. They would add together and make 2y. So would it help us to eliminate just that one term that just had x to the first power in it? No, okay? So substitution might be a more friendly option in this case. So if we substitute, it means anywhere we see y, we can replace it with the other equation. So, for example, when you look at the first equation, you see this. If I'm going to substitute the second equation into this, that means, since the second equation says y equals negative 3x plus 4, Basically, anytime I see y, I can replace it with negative 3x plus 4. So I'm going to come back to this equation. I'm not going to think about using y anymore. Instead, I'm going to use that substitution idea and replace y with 3x plus 4. Okay. Now, what am I going to have to do at this point to finish getting my solution? Okay. Good. We're going to set it equal to 0. Hopefully it factors. If it doesn't factor, we'd have to move on to something more complicated, like completing the square or the quadratic formula. Okay? So I'm going to move both of these terms by adding their opposites here to the other side, so that I'm going to have 0 is equal to x squared plus 6x plus 5. Is it factorable? Did our plan work? Yes, sorry. If you do negative b over 2a, you're finding the vertex. Yeah. And we're looking for the solution. So we're looking for x-intercepts. Eric? X plus 5. So it factors nicely. And so what do we get as our solutions here? Raven? Good. And we get that by setting each factor equal to 0 separately, right? So x plus 1 equals 0 gets us the negative 1. X plus 5 equals 0 gets us the negative 5. Now, what is this? Do we just put parentheses around this and say, oh, I found the point where they cross. It's negative 1 comma negative 5. Is that right? Good. We have to plug x values back in to get y values. And how many x values do we have? 2. Now, with lines, this never happened because what was the maximum amount of times 2 lines could cross? Well, 1 or infinitely many if they sat right on top of each other, right? But there wasn't kind of this option of 2 because we couldn't bend the line or else it was no longer a line. Now, what 2 objects would we be looking at here on a graph? A parabola and a line. Is it possible that they might intersect at 2 points where we'd need 2 separate x coordinates and y coordinates that go with each of them? Okay, can you picture in your head some way that a line could intersect a parabola in 2 places? Okay, so our hope then is to figure out one point where it's negative 1 comma something and one point where it's negative 5 comma something, plugging back in those x values like Claire said to get those y values. Okay? And we can plug back into either equation. Does that answer your question? All right. The reason we can plug back into either equation is because, remember, we're focusing on the places where they intersect. So the points that we're finding should be on the line and on the parabola because it should be the place where they intersect. So maybe I'll choose the linear equation because I think it's easier to plug into. Right? So when I plug in negative 1, I get 3 plus 4, which is 7. And you guys check my arithmetic because we know sometimes I mess it up. All right, and then when I plug in negative 5, you get 15 plus 4, which is 19. Does that look okay? You guys got the same answers I got? Okay. So we would say that we expect there to be 2 solutions to this system. Okay? In other words, we expect this line and this parabola to intersect at 2 points, specifically these 2 points listed. Julia, did your question get answered?
Yeah, so, okay. Well, so you can't plug it back in, like, you can plug it into the x squared plus x plus 5.
No, because that was like a combination of the 2 of them. Okay. And if we plug negative 1 and negative 5 in here, we'll get 0 because that's how we figured out what those were. Cody?
Why can't you say, like, switch the x values and y values around, so negative 1, 19, negative 5, 7?
Okay, so remember that we solved for 2 x values. 7 was only obtained when I plugged in negative 1. So remember, there's some parabola on the graph, right? And it has some point negative 1 comma 7. This isn't a good picture. It should be like this maybe. Like negative 1 comma 7 over here. And then at negative 5 comma 19 is up here. If I just flip-flop the values, I might have another random point on the graph, but it's not going to be on my parabola or my line. Okay? And that means that line's going through there, someone like that. That's something I would expect, some kind of idea of what's going on. So let's look at it graphically. Okay? So let's take out our calculators. Let's plug both of these equations into the calculator. So we're going to type 1 into y1, 1 into y2, and I'm going to show you guys on the calculator how to find where things cross on the graph. Okay, so just like your calculator can do a maximum, a minimum, zeros, it can also calculate the point where two different functions cross. Okay? Let's see. That's fun. Okay. All right, so first, if your calculator looks anything like mine, I want to clear this screen. I'm going to go to my y equals, and I'm going to clear out any equations that are in there. If you want the equations that are in there for some other purpose, just go make the equal sign not bold, and it won't show up on the graph. And make sure that all your plots are turned off. So up at the top, make sure none of them are bold. So you see, I have some work to do. I don't need this anymore, so I'm going to clear it. And up at the top, I'm going to unbold that plot so that right now, nothing is being graphed on my calculator. Okay. Then I'm going to go and I'm going to type in the two equations that we were looking at. Okay. So go type in the two equations from the notes. So it was x squared plus 3x plus 9. Sorry, Matt. And then the second equation was negative 3x. Remember to use the negative and not the minus. Plus 4. Did I type them in correctly? You guys have them right in front of you, so that's why I'm asking. All right, now before I push graph, I'm going to go zoom, and I'm going to choose choice 6, the standard window, the 10 by 10. Not because I think that's the best, but because the last thing I graphed was stats, which would have been like some crazy scale to fit my statistics. But now I at least have an idea of what's going on. Clearly, this isn't the best graph. I really don't need to look at any of this stuff over here. I really need to see where the line is intersecting the parabola. Okay? So do you see on my x-axis, I can ignore like a bunch of these positive numbers. So I can change my x maximum to be something smaller. Okay? I can change my y minimum to be something much larger, but I need to increase my y maximum to see further up. Okay? And we've already solved it algebraically, and we think what was one of the intersection points that was higher up? Okay? Yeah, so I know I at least probably have to be up there if I did my algebra right. So to change your window to your own custom window, go to Window, and change the things that you want. So my x minimum, fine. My x maximum doesn't need to be 10. Maybe it only needs to be like 2 or something so I can see the x-axis. My y minimum, I'm going to move it way up to like positive 2, so I'm not even going to see the x-axis. And my y maximum, I know I need it to at least go up above like 19. So maybe I'm going to try like 24 or something. I don't know. All right, now I'm going to press graph and see if I did a good job. Better? Better. You might still have something better. You could choose some other things. So right now what we're going to do is we're going to figure out how the calculator can calculate intersection points, and we're going to see if we were right. So one small, not problem, but just takes a little more work. It's kind of like calculating the zeros. You can only do one at a time. You know how you have to like go all the way to 1, 0, do the left bound, the right bound, and figure it out? Then if you want to do the other one, you have to go to the other side and do the left bound and right bound. Same idea here. You can find one intersection point, and then you have to separately go and find the other one. Okay? And a small reminder that when you're tracing a certain graph, which is really important now that we have two on the same graph, left and right buttons trace you along the graph that you're on. Up and down buttons jump you from one curve to the other. Does that make sense? So if you're pressing up to go up, you're not going up. Your cursor is just switching back and forth, one between the line, then back on the parabola, then back on the line, back on the parabola. Make sense? Okay. So every time we want to calculate something on the graph, we get it at the same place. So I'm going to go second, and I'm going to push trace, which is the calculate menu. What do you think we want to calculate today? Intersection. So choice 5, intersect. Notice it doesn't say left bound and right bound anymore. It says first curve. So what it wants you to do is travel along the first curve that it puts you on. So notice it put me on the parabola, probably because my parabola was entered as the first equation. I'm not going to push up and down, okay, because that's going to switch me. I don't want to switch right now. So I just need to push left and right to travel along the parabola till I get as close as possible to the intersection point I want to calculate. Okay? So I'm going to go ahead and calculate this higher one first. So I'm traveling to the left to get as close as possible to where I think the intersection occurs, and I press enter. So what I'm telling the calculator is, this is where I think the intersection happens when I look at the first curve. Then it says second curve. It has already switched the curve for you. You can't tell because it's sitting right on top of where you marked it on the first curve. If you thought that was the intersection on the first curve, hopefully it's like in the same place on the second curve or you weren't picking the right things. So you can just press enter again. And then it's going to say, do you want me to guess? Yes, or we wouldn't be doing this, right? So press enter one more time. And then it will calculate the intersection for you. So you can see that the intersection point is at negative 519. That's what we got algebraically, right? So we did a good job. Now go ahead and find your other intersection point and make sure that it's at negative 1, 7. So you're going to go through the same process, okay, and make sure that you get that same thing. But you're going to have to scroll left or right now to sit on the other intersection to calculate it. I'm going to do mine while you guys are doing yours. So I got negative 1.7 like I thought we would get from algebraically. Pretty good. Okay, so you guys should have just learned like a couple things. One, you should have taken your solving system skills to like a new level, right? It doesn't matter if the system is a little more complicated. That substitution elimination idea still works. Okay? You just have to be a little smarter about what you plug in where, because you can't just eliminate one thing and have everything else pop into place for you. Okay? The second thing is, now it would be fair game for me to ask you guys to find intersections on the calculator, right? So after this quadratic unit, you guys should be able to find solutions on the calculator, or x-intercepts, zeros, okay? You should be able to find maximums or minimums. You should also be able to find places where things intersect, right? You learned a lot of skills on the calculator, and you should be able to do all of those things off of the calculator also by hand with the stuff you know about how a parabola works, okay? Are we okay with this idea? Yeah? All right, so we're going to have you guys try some more solving systems. All right, so why don't you guys try part B? So first, people started substituting, okay, to solve the system. And people ended up with this quadratic. And was your quadratic factorable? No. Okay. So somebody asked, if it's not factorable, does that automatically mean there are no solutions? So can a quadratic have solutions, real number solutions, even if it couldn't be factored to solve it? Yes, right? That's why we use the quadratic formula. If everything was either factorable to solve, and if it wasn't factorable, there was no solution, then we wouldn't have to know the quadratic formula or the completing the square method or things like that, right? So it doesn't automatically mean that there's no solution, okay? But it means that if there is a solution, we're going to have to do a little more work than factoring to get it. So what should we try? Quadratic formula, sure. Now we can make decisions. So what is this telling me? So if this quadratic was solvable, it would have imaginary solutions. But when we're looking for solutions of this system, remember, we are physically looking for places where the line and the parabola cross on our real coordinate axis with a real numbered x-axis and a real numbered y-axis, right? So if we're getting this, what does that tell us? So this quadratic would have imaginary solutions, but what does that tell us about this system of equations? That there's no solution, okay? And so like Dylan graphed it on his calculator, and if you graph it, you'll see that the parabola is down up here and the line is down below it, and they never cross, okay? And that's why we have no solution. We wouldn't try to find the imaginary solutions, because that means you would be trying to say that on an xy coordinate plane with real numbers, you're trying to say, oh, they intersect at 5i, 3, but 5i, 3 doesn't exist on the real number coordinate plane, right? Okay, so once we get here, we can say no solution.
On my calculator,
Mhm.
it was like, if there's really more explained, it was like half of a parabola, and up and down like.
Oh, check your, that's a cubic, so check what your exponent is on your. All right, any questions about the no solution? Okay, so I'm still going to use substitution. I saw elimination being used, but it only worked when you eliminated and then you substituted back in. Okay? Right? Because then we're going to end up here with 2x squared plus 6x, and the 7s will cancel out. So is everybody okay with once you get everything on one side, you have a quadratic like this? Cody?
Wait, so like if you took out the x squareds and you substituted 3x plus 7 for y, could you still do that?
3x plus 7 for y.
Like you put 3x plus 7
Yeah, but you still have something like this, right? Yeah. So your equation would be different here, but then your solutions should still be the same. Because once I factor this, I'll take out 2x. You will only take out x. And when I set my factors equal to 0 and see what my options are, this is like 2 times x plus 3. The 2 is not going to be equal to 0. It's 2, right? It's its own factor. It's already determined it's 2. I can't change it because it doesn't have a variable. It's not going to be the one that makes something equal to 0. But the next factor is x by itself. X could be equal to 0. Okay? And the next factor is x plus 3, which could be equal to 0 if x equals negative 3. So this gives me two x value options, 0 and negative 3. Okay? And is it possible that these two shapes could cross twice? Yes? Yeah. All right, so then kind of hoping that I'm going to get 0 and then negative 3 something, and I'm going to be able to figure this out. Okay? So if we plug 0 into either of those equations, what are we going to get? Should be an easy one to plug in there in standard form. Yeah, 7, okay, because all those terms that have x in it will just turn to 0. Then if we plug in negative 3, I would get 9 minus 27 plus 7, which is negative 11. Yeah, someone confirm I'm good by arithmetic. Which tells me these two parabolas cross at 0, 7, and negative 3, negative 11. Yeah.
How do you find the x equals 0 then?
So I factored and set my factors equal to 0. So it's the same idea as if, like, you factored like this. You set this factor equal to 0 and this factor equal to 0. You guys can't forget that just because x isn't in a parentheses with something, it still is a factor, and it could still be set equal to 0. Okay? And you could even do it as 2x equals 0, and then when you divide both sides by 2, you'd get x equals 0. Okay? But if there's a variable in a factor, it should still contribute to getting that 0. So it should still be set equal to 0. Any questions on solving these algebraically before we look at the last thing that we're going to do? So the last thing we're going to do is a system of inequalities. So how is the problem going to change? Helen? Different lines and shading. And we're not going to be able to do it algebraically because how do I explain to somebody, oh, it's all these points in here algebraically? That's really hard. So we use graphs to represent our answers on inequalities because we have like, oh, this shape's a boundary, and it's just this stuff in between them over here. Okay? So it's a system of inequalities. Since it has like this infinite number of answers, we're going to have to represent our answer on a graph. Was there a question that needed answered? Monet, did you have a question or no? Okay, sorry. All right, so let's talk about getting these on the graph. So first of all, what shapes are we graphing? Parabolas. Good. First parabola. Concave up, concave down. Up. Okay. So we're focusing on it like we just want to put this on the graph, and then I'll deal with like if the boundary's dashed or solid, or which way the shading should be after I at least get the boundary line on the graph. So let's say I want to graph this by hand, because I should be able to. how am I going to figure out where to put some information on my graph? Good. Good. So, Preston said find the vertex, and Julia told me how to do that. We're going to do x equals negative b over 2a. So it's not going to be that pretty in this case, but whatever. It's going to be negative 5 over 2 times 1, which is going to be negative 5 over 2, or negative 2.5. Okay? So that's my axis of symmetry for one of my parabolas. Then I need to plug 2.5 in to figure out what the y value is. And you guys can go ahead and do this on the calculator. The reason we're graphing this by hand is because you guys have to know how to graph by hand, and I'm not sure that everyone's up to speed. It was at the beginning of our unit. All right, so what did you guys get? What is it? 7.75? 10.75? Yes? No? Okay, so let's check. Oh, negative. Sorry. So negative 14.25? Okay. Sorry, I tricked you guys. I didn't mean to. All right, so negative 2.5, negative 14.25. I'm going to number my y-axis by 2's. Okay. I'm just going to mark that on here one time so I know that. There it is. And then where is my graph concave down or concave up? Up, okay, because the x squared is positive. And how am I going to get some other points besides the vertex point for my parabola? Good. I can plug in anything I want. I just don't want to get too far away from the axis of symmetry, or else the numbers will start getting really far away from wherever my vertex was vertically. But if I plug in 0, okay, I would get negative 8. 0 is an easy number to plug in standard form because that becomes 0, that becomes 0, and then we have negative 8. So for me on my graph, that would be here. And I want to make sure I mirror it on both sides. So this is my parabola. Now as I fill it in, I'll think, should the boundary line be solid or dashed? Okay. Oh, sorry. All right. Then where would the shading be for this parabola now when we look at the inequality? So this was really y is greater than or equal to x squared plus 5x minus 8. So do you think it should be this region within the parabola or around the parabola? Around the parabola? Okay. So let's test a point and see if you guys are right. So let's go ahead and test 0, 0. If we plug in 0, 0, which is right here inside of the parabola, we would get 0 is less than or equal to negative 8. Is that true or false? Yeah, sorry, greater than or equal to negative 8. True or false? True. So 0, 0 is a solution, which means should the shading be within the parabola or around the parabola? Within the parabola, okay? So this parabola would be shaded in here. Yes. No, shading is the same for greater than or equal to or greater than. It's the boundary line that would be drawn differently if it wasn't equal to. It would be dashed instead of solid. Okay? All right, so the next inequality is y is less than negative x squared plus 3x plus 4. So we want to go through the same procedures to get this on the graph. So you guys go ahead and start it on your paper. I'm going to start it up here. We'll see if our calculations are the same. So I believe the vertex is at 1.5, 10.75. Is there anyone that can confirm? No? What did I do wrong? For the 10.75 part? All right. Oh, because I didn't do my negative. Thank you. 6.25? Yeah. Okay. All right, so let's plot that vertex at 1.5, 6.25. So 1.5, 2, 4, 6.25. Now this parabola should, by expectation, be concave up or concave down? Concave down. And to get another point on the parabola, I should do what? I only have the vertex point right now. I need some points on the side to know how wide to draw this parabola. What should we do? What did we do last time? What have you done before to get points once you have the axis of symmetry in the vertex? Plug in, yeah, and you can plug in anything. 0 is just really handy when you have an equation in standard form. Okay. So when I plug 0 in here, I'm going to get the point 0, 4. And this time, the real inequality just said less than, so it should be dashed. And should the shading be within the parabola, so kind of underneath the arch, or it should be around the outside, kind of above the rest of the parabola? Y is less than, so it should be below. And if you weren't sure, again, you could plug in 0, 0. If you plug in 0, 0, you'd get 0 is less than 4, which is true. And 0, 0 should be part of the shading in there. So this is what would happen. So your solution to this system of inequalities is what? Sorry, Monet, yes. Plugging in 1.5 in here, and then the first time I did it, I forgot to include my negative at the beginning, so if you got something different, check that. But Raven, were you going to answer our question? Okay. Good. It's the area that's double shaded because solutions of systems are the points that meet both requirements. So that for us would be all in here. Okay. Now let me ask you guys, obviously I can pick anything kind of in the shaded region and it's a solution. What about the boundaries? Okay. Is the blue boundary line, does it include solutions? Yeah. What about if I pick a point here on the red boundary line? Is it a solution? No, it's part of the blue shading, but it wouldn't be part of the one that I graphed in red because the boundary line was dashed for that parabola. So just be careful in understanding which parts are the solutions and what the limitations are of that. Claire, question?
For the red,
Uh-huh.
since it's not greater than or less than or equal to,
Uh-huh.
will it matter when we graph it if the dots are open or closed?
They're technically open, but I symbolize that through drawing the whole thing dashed. So these would technically be open because everything on the boundary is dashed. But if you draw for me a dashed line for the entire graph, I would understand that you're saying everything along this graph is a boundary but is not included on the points. Okay? Any other questions about that? All right. So now we're going to have you guys work on questions you might have